Hey everyone, welcome back to Chem Story. When we study stereochemistry, one question that comes up a lot is, how many stereoisomers does a given molecule have? At first, it might seem like we can just use a formula to figure it out. But in reality, some molecules with molecular symmetry don't follow the rule as expected. That's because molecular symmetry plays a huge role in determining the actual number of distinct stereoisomers. So today, we're going to break down how to count stereoisomers the right way and look at cases where symmetry reduces the expected number. Let's get started. One common way to figure out the number of stereoisomers for a molecule is by using a simple formula. The total number of stereoisomers is 2 to the n, where n is the number of chiral centers. For example, if a molecule has one chiral center, 2 to the 1 gives us 2 stereoisomers, one with an R configuration and one with an S configuration. If there are 2 chiral centers, 2 to the 2 gives us 4 stereoisomers. And if there are 3 chiral centers, the number jumps to 2 to the 3, which means 8 stereoisomers. At first, this formula seems pretty straightforward, but here's the catch. It only works if all the stereoisomers are actually distinct. In reality, some molecules have internal symmetry, which makes some stereoisomers identical. So the actual number of stereoisomers can be less than the formula predicts. That's why just using the 2 to the n rule isn't enough. To get the correct number, we need to draw out the structures and check for symmetry. Now that we know why symmetry matters, let's dive into some real examples and see how this works in practice. Let's start with a simple example, 2-bromo-2-butanol. This molecule has just one chiral center, so if we apply the rule, 2 to the 1 gives us 2 stereoisomers. Since there's no internal symmetry, these two forms are completely distinct, one with an R configuration and the other with an S configuration. Now let's take a look at 3-bromobutane 1,2,4 triol, which has 2 chiral centers. If we apply the rule, 2 to the 2 gives us 4 stereoisomers. And when we actually draw out the possible configurations, we see that there are indeed 4 distinct structures. Since this molecule doesn't have any internal symmetry, all 4 stereoisomers are unique, just like the formula predicts. But, as we'll see in the next example, symmetry can sometimes reduce the number of possible stereoisomers, making things a bit more complicated. Now, let's take a look at butane 1,2,3,4-tetrol, another molecule with 2 chiral centers. If we just go by the formula, 2 to the 2 should give us 4 stereoisomers. But when we actually draw them out, we see something unexpected. We don't get 4 distinct stereoisomers. Instead, we only end up with 3. So what's going on here? The answer lies in internal symmetry. Some of you might be wondering, where exactly is the mirror plane? At first glance, it might seem like there's no internal symmetry at all. And that's a great question, because spotting symmetry in a molecule isn't always straightforward. To figure out whether symmetry is present, we need to look at the molecule in its most symmetric orientation. Instead of viewing it in the usual stable zigzag conformation, we should look at it in the orientation that shows the most symmetry. That's how we determine whether a mirror plane exists. In this specific arrangement, you can clearly see an internal mirror plane running right through the molecule, splitting it into 2 identical halves. And that's exactly why B and C are actually the same molecule. Because of this symmetry, what we first thought were 2 different stereoisomers actually turn out to be just 1. This reduces the total number of unique stereoisomers from 4 down to 3. This is a great example of why just assigning R and S configurations isn't enough to figure out the actual number of stereoisomers. If we don't draw out the molecular structures and check for symmetry, it's really easy to overestimate the number of possible stereoisomers. Now, let's look at a more complex example. Cyclopent 4N 1,2,3 triol. First, let's draw the structure of the given compound. We can see that C1 and C3 are chiral centers. The question is whether C2 can also be considered a chiral center. At first glance, it's easy to think that C2 is not chiral, because the substituents on either side of the ring look identical. And yes, in some arrangements, it's not a chiral center. However, if the substituents on C1 and C3 are mirror images of each other, making the entire molecule symmetric, C2 is called a pseudochiral carbon. So depending on the structure, C2 can either be a pseudochiral carbon or not a chiral center at all. In these cases, it's much more accurate to draw the structure rather than just applying the 2 to the n rule. When we actually draw out the structures, we might expect 8 possible stereoisomers. But here's the interesting part. When we actually analyze the structures, we find that instead of having 8 distinct stereoisomers, we only end up with 4. Here's why. When we map out all 8 configurations, some of them turn out to be identical due to symmetry. Specifically, A and E, B and D, C and G, and F and H are the same molecules. So the number of unique stereoisomers gets cut in half, reducing it from 8 to 4. This shows why it's important to actually draw the configurations. If we just followed the 2 to the n rule, we would have overestimated the number of stereoisomers. So the key takeaway here is that symmetry can reduce the number of distinct stereoisomers, and it's always a good idea to draw out the structures rather than just applying the rule. I hope this breakdown was helpful. That's it for today's lesson. Thanks for watching, and I'll see you in the next one.